My name is Ruggero Maria Santilli. I am the chief scientist and the president of iFuel Inc., the company that owns all rights on the new fusions known as intermediate controlled nuclear fusion without any radiation or harmful damage to the environment, also known as intermediate fusion, and they are known with a nickname of warm fusion. In this movie, we shall present the essential elements of the third Hadronic Reactor that was built by iFuel Inc. thanks to funds from China, specifically from Professor Wei Kai, that very generously supported the construction of this third reactor. In this movie, we shall present a review of the status of our efforts in the construction of the third Hadronic Reactor as of today, December 29, 2011.
Hi, I'm Chris Lynch. I'm the mechanical designer for the third Hadronic Reactor. I designed it in collaboration with Dr. Santilli.
Hello, my name is Don Roach. I'm the metal fabricator. I'm a certified 6G pipe welder. I worked in collaboration with Chris here from his designs and his blueprints, and I built the Hadronic Reactor.
My name is Fred Gridley, and I worked in conjunction with Dr. Santilli to design and instrument the electronic controls and monitoring equipment for the Hadronic Reactor.
Hi, my name is Michael Rodriguez. I'm the electronic engineer for iFuels Inc. I made all the electrical connections for the Hadronic Reactor.
My name is Gino Amato. I'm the Director of Procurement for iFuels Inc. and I was responsible for procuring all the components necessary to build the Hadronic Reactor.
My name is Katarina Kuinova. I am in charge of bookkeeping of EcoPlanet Inc., who is subcontracting iFuels Inc.
I'm Erin Wally. I am in charge of the logistics for this project.
I am Carla Santilli. I am the administrator and the treasurer for iFuel Inc. and EcoPlanet Inc.
This is the third Hadronic Reactor that we built for the new type of fusion. The preceding two are described in preceding movie, and therefore they will not be treated in this informal movie. This third reactor operates at 1000 psi and produces steam. Consequently, for our safety, we have placed the reactor inside a metal container, so that in the event of any loss of steam at supercritical temperature, there is no injury to any of us. But thanks God, so far we had no leak of any type. The main component of the reactor are inside, and here on the outside, what we see is the control, all the various controls and recording systems that we will describe them in a moment. Then we have the power unit, which is an Amertec AC-DC converter, which we use at 50 kilowatts. Here we see a compressor that to maintain the pressure inside the reactor, and then we have a computer and other equipment.
We have the current transformers. This is disconnected, they're turned off. The current transformers that measure the current on the 480 volt leg. We have our power light. We have isolated the voltage that feeds the meter and the light, so we get a true representation of only the current that is being used by all the equipment in the reactor. For safety, when we have system energized, we have the light that shows it's energized. Our meter shows the voltage for each leg. This is a very accurate meter that measures our voltage, our current, our kW, all the power that is consumed by all the equipment. We have several power requirements in the reactor, so we are distributing the main power from this box. The 480 volts feeding from this box goes to the Ametek power supply. We also take the feed from this box to this transformer that brings the voltage down to 240 volt 3-phase. It is followed up and redistributed at lower voltage to the other equipment through this panel, and that feeds the lower voltage equipment plus all of the controls. Everything is wired per the code, and by feeding it through this way, we know that everything, that all the power consumed is being recorded by this meter. A very important aspect in the operation of this reactor is control and measurement of the parameters. We have integrated this touchscreen monitor with a programmable controller, so we can monitor and control all the functions of the reactor. We have display icons that can switch on and off via the touchscreen, and we have a data logging screen so we can record and view the data real time or scroll back and forth to look at the log data. The log data is also capable of being written to a USB flash drive for later downloading and viewing and integrating into a spreadsheet. We also have the availability of an Ethernet port where you plug your Ethernet cable in and you can view real time via the internet the information displayed on the screen or the operating conditions of the reactor. This is a programmable controller that will interpret all of the data signals from our instrumentation and also control the processes. We have the power supply to supply power to the transducers. This makes all the decisions. This communicates with the touchscreen via data link. We use the variable frequency drive so we can accurately control the flow rate of the circulation pump and also of the refill pump. And these provide data to the computer so that we can log and record and view the real-time flow rates, and those are also part of the data screen. These give us very efficient control of the motors. And there again, all that information is available on this screen and is available for download, and these screens can be viewed via the internet.
This is the arc power controller. It controls the position of the electrodes, the arc intensity, the arc voltage. It has 22 different parameters that we use to adjust for different hadronic fuels. The meters here are for monitoring temperatures. We've actually taken a lot of things and put them in here so that everything is all data recorded. We have indicator lights here to indicate power is on, that the electrode is in position, it's running in automatic. A few warning lights if we have problems with electrodes and whatnot. Pump on indicator lights, control switches, emergency stop, of course. And this switch turns the machine on and off. This is the air compressor that we use, only when we're using air as a hadronic fuel. It maintains the pressure in the vessel and the airflow through the vessel.
This is the hadronic reactor number 3, which is located inside the metal container that we have shown before. The nuclear fusion occurs in the interior of this metal chamber, as described in a moment by Chris Lynch. We are testing this reactor with a variety of what we call hadronic fuels, namely fuels that they are suitable for nuclear synthesis of our type, which is without any harmful radiation. The first hadronic fuel that we use is deuterium, because we have a fusion between deuterium and carbon, which, if it occurs can only produce nitrogen absolutely without any harmful radiation, particularly in the absolute absence of neutrons and neutronic and other very harmful radiation. Or the fusion does not occur. In this case, there cannot be any harmful radiation because the power that we use is millions of times short of the power and energy needed to smash nuclei so that eventually we produce harmful radiation. Another test that we do, we use for hadronic fuel air and of course the carbon of the electrodes. We use air because of two reasons. Reason number one, because it will burn with carbon, therefore producing heat without harmful radiation. And secondly, because the oxygen contained in air can produce silica once under our type of fusion with carbon. Again, either oxygen and carbon fuse together in our technology to produce silica. In this case, there cannot possibly be any harmful radiation whatsoever, none. Or the fusion does not occur, and there is no possibility of harmful radiation. In the first case, when we use deuterium, then basically the only byproduct is heat, and that is extracted by a cooling system based on water. In the second case, please note that the hadronic fuels are very simply air and carbon. And heat is utilized via a cooling system based on a heat exchanger based on water. I repeat, in the second case, the use of air and carbon produce combustion of oxygen, as well as, in addition, the synthesis of silica, therefore producing a substantial amount of clean energy without any harmful radiation. The water, in this case, is used to utilize and extract the heat from the reactor.
Hi, Chris Lynch again. This is the third hydronic reactor, and it consists basically of a high-pressure vessel with water jacket and coils inside and outside the vessel to completely capture as much of the heat generated from it. The electrodes are controlled by this motor at the end, and that controls the position of the electrodes inside. This is the step-in motor for the completely automated control of the arc. These are the DC power input cables and either gas or air input valves, pressure transducers and other control equipment. All the plumbing you see around it is just for the water flow. This long beam on the top is to support the flanges when we open the vessel for maintenance and changing electrodes. As you can see here, these flanges are extremely heavy, thus the heavy beam.
The main and most fundamental data for any test are two. First, the very accurate measurement of the used power, which is done by this calibrated watt meter, and that has been re-verified, certified by the manufacturer, controlled by us. Then we have to go on the other side of the reactor to see how we measure the power out. I want to indicate the main principle of operation when we use air as hadronic fuel and water as a cooling system. The principle is essentially the following, that we have a steady flow of air entering into the reactor, and which acquires very high temperatures, not only because of the arc, but also because of the nuclear fusion. Then this air is then mixed with the steam produced by the reactor to power a turbine, as we indicated in one of the next section of this presentation. So keep in mind that the heating up in this case of the water in this upper throat is done by both, not only the water that flows through the internal and external jackets, but also by very hot air which has been mixed with and which comes out of the reactor. The measurement of the power output is done as follows. We use a throat which is filled up with ordinary tap water that contains accurately measured volume of ordinary water. We pass this water through the reactor, through both the internal and the external chamber, and the water is released back into the throat. And then we measure the delta T, namely the initial temperature at the beginning of a test, and then the final test, the temperature at the end. By having an accurate measurement of the delta T, since we know accurately the volume and the weight of the water, we can measure rather accurately the energy which has been produced. Keep in mind that not in this case, but in ordinary operation, which you will see in the next segment of this presentation, when we use the reactor to power a turbine, then the air as a primary function as follows. That air is released inside the reactor when we use air as hadronic fuel. Then the air is coming out of the reactor at very high temperature, is mixed with the steam and brings the steam to supercritical temperature, and then the combination of very hot air plus steam is released into turbine to power an electric generator.
To do the energy output measurements, we're keeping it very simple. We have a known volume of water. We're passing it through the vessel and then right back into the container again, and we measure the temperature rise over time of this water, and it gives us a direct reading in BTUs. Now, in the process, we have two pumps underneath. We have one flow meter, which measures the flow of the water, the flow rate through it. We have thermocouples measuring the output temperature of the water, some analog gauges also measuring the water, and another thermocouple measuring the water in the tote. Since we ran this test with air, we had the air flow through the chamber. It comes out this line, and to capture the heat from the hot air, we ran it right into the tank and bubbled it through the water to capture the heat in the water. This is a rudimentary steam engine we made to be run by the hadronic reactor. It is no longer in use at the moment because we are using a screw compressor, which is much more efficient. This was an initial test.
Today is December the 21st, 2011, and this is a recording of one of the several tests that we do. This shows the control room with Fred, our master electronic technician. Want to show now the view of the various controls that are all in automatic recording and computerized for storage. This is the control of the arc, that you can see the voltage, the various operation. Also, you can see from here the amps and the amps and the voltage to see that the arc is indeed stable. Now I want to show you the reactor is inside for safety because it's producing a steam. so for our own safety. Here is the steam that is producing, and you can hear the noise of the turbine while it's turning under the steam. You can hear. Pay attention to the noise of the turbine. It's going up in RPM, and what we use for fuel is air and water. Water that is released into the reactor, however, at ambient temperature. We are not yet recirculating hot water. We just let it go into steam at this stage, but the final version will require the recirculation of the water, so that we don't need. This will be an increase on the efficiency, because now most of the energy is used to heat up the water all the way from ambient to about 300 degrees Fahrenheit. That's a major loss in energy. Once we recirculate it, we will bring it back just below the threshold level of the boiling. And so the conclusion we can have in this case is a dramatically increase, significant increase in the efficiency. Now we are increasing the flow of air. Listen to the noise of the turbine. It goes up in RPM, as well as the increase of the smoke. And this by just increasing the flow of hot air and keeping constant the flow of the steam. Always remember we are operating at 1/3 of the actual pressure and data that for operating this unit. And this is an example of the electrodes that, of the anode actually, that we have extracted from after a preceding test. And this is what we call the pancake, that is mostly silica and carbon as per chemical analysis done by the laboratory of Gamma Technology in Princeton, New Jersey. It is a very solid, as you can see, it's a very solid object. And it is high consistency, and you can see visually the silica embedded with the carbon, and it's a very strange solid which is created by the reactor that we are now analyzing. We are waiting for chemical analysis as of today. I believe they will be shipped today or tomorrow from the laboratory in New Jersey. But essentially this is evidence that we have indeed synthesized silica. And therefore, this is evidence that indeed we have unlimited energy available, clean and environmentally acceptable, without secondary radiation, subject to funds and subject to the resolution of rather significant number of the engineering and technological problem, including very advanced power unit of high frequency, pulsating, high voltage, including high pressure. This technology should go to 3,000 psi or 5,000 psi, not only at 1,000, to have significant and other technological advances.
We have a printout here of the information that was collected on the data monitoring function of the touchscreen monitor. This information is printed out in a text format that can be brought into any spreadsheet program and formatted. It provides you all the information, your time and date, your temperature of the water in, temperature of the water out, the vessel temperature, all of this information. You can do calculative functions where we can do the volts times the amps to get the DC watts for the electrodes, and it gives all you this information in a usable format that is then able to be stored or manipulated or plotted as graph from any spreadsheet program.